Welcome back, guys. We're going to talk a little bit about dielectrics. So the first thing you should know about dielectrics is they're usually insulators. Um, because what you do with them is you're going to take them and you're going to take your parallel plate capacitor and you're going to insert a dielectric in here. So you got your positive on this side. I always like to make the positive on the left for some reason. You're going to insert a dielectric between your two plates with some dielectric constant epsilon or permittivity epsilon. So you want an insulator in there, so because if you put a conductor in there, if it touches both plates, it's just going to carry the charge across. So they have to be insulators. And what they do is, I guess I shouldn't draw the epsilon here. Let's draw this again. Let's draw this bigger. So here's your dielectric in the middle. So normally the field goes right to left. So a dielectric, you can think of it as several small dipoles inside. I'm just going to draw two sets for each one, just for to be expeditious. Alright, so from the macroscopic scale, you expect the electric field to go from positive to negative, right? But if we look at so you should have fields, I guess, that look like this throughout. Right? That's positive there. So, but what about inside of our little dipole pairs? Because our insulator gets polarized by the electric field, right? The negative charges get pulled to that side, and the positive charges get pulled to that side, and the negative charges get pulled there, and the positive get pulled there. But because it's an insulator, charge can't flow freely. So we should write there. Put that down. But it can be polarized. So that's what we're doing here. We're creating little polarizations. So now if we look at the electric field inside each little pair, it's actually going to go that way. Creating this opposing electric field. I'm not sure what the name for these guys is offhand, but I'm going to just call them polarized pairs for now. So the polarized pairs create an opposing electric field. And so this has the effect of weakening the overall electric field in the center, inside the dielectric. And the capacitor and the dielectric. So why do we put these in there if they weaken our electric field? Because that seems like it's counterproductive, right? Well, let's think of it this way. Because one of the goals of a capacitor is usually to store the most charge with the least amount of energy, right? Let's write that down. You want to easily store charge, right? And let's take our equation of Q equals CV that we looked at earlier, and we're saying I want to get more charge for less potential, maybe, or less electric field. Let's slide this up. So if I say V equals electric field times distance inside the capacitor, let's rewrite this as C ED. And the equation for capacitance is, we're going to use epsilon A over D, which we could also write as kappa epsilon naught A over D. So I guess let's use this kappa one. And let's put that in. So this is now going to be kappa epsilon naught A over D times electric field times distance, right? So these D's cancel. So why is this useful to us? Because what we've done is said if I put a given charge on here, right, or if I apply a given electric field, it's hurt it, right? Which seems like it should make our charge go down. And it does. Because you have to remember the way this is mostly applied is this is usually going to be applied in a circuit. So we're going to have some circuit with a resistor and a capacitor, because you always have to have a resistor in there. So our voltage is actually the thing that's fixed. So the voltage is fixed. So if I say, let's say V, maybe is a better way of solving this, equals Q over C for when the capacitor is fully charged, right? Now this V is fixed. So in actually putting the dielectric in there, I've caused this kappa, which is, wrong way. Kappa is greater than or equal to 1, always. So by putting this kappa in here, in this equation, I've caused this guy to go up, right? Which means that to get the same ratio, I have to increase the charge. And so I'm being allowed to store more charge for the same potential. So it lowers my electric field, yes, but in lowering my electric field, it lowers my potential across the capacitor. So, which then allows me to store the same charge, or more charge for the same capacitance. Alright, let's put a stop to this one before it gets too long, and I'll see you in the next one.